2 new companies by the end of this talk. And of course, Paul Dix, which is legendary founder, is here from InfluxDB, incredible builder, evidently not great investor, but thank you, Paul, anyway, for the money. So I spent the last 10 years up and down the stack in what I call friends-driven development, which means that I have very smart friends. I tag along with them, and I sort of take the credit for whatever they do. So at the very unlikely intersection of all these acronyms, you'll find my past lives. So I trust you to be able to Google. So if you want to learn what I did before, please go ahead and do so. So today we're going to talk about Bauplan and basically how we built this with a relatively small set of resources and the lesson that we can take from building data infrastructure at scale in 2025. So what is Bauplan? Bauplan is a lakehouse for engineering teams who want to treat data like software. We're going to see what that means in this talk, but the general idea is that you can think of data with the same abstraction, the same mental model that we use to think about software, and that is good for everybody. It's good for people using the system, and it's good for us building a system that people use. So the talk is called Speedrunning the Lakehouse. So speedrunning is kind of like our main metaphor today, but I want to know how many people know what speedrunning means. Can you raise your hand? Okay, so many of you. So if you know what speedrunning means, you're awesome. It doesn't matter what people in high school used to say. For people that do not know what speedrunning means, speedrunning is the challenge of finishing a video game as fast as possible. So the world record for Super Mario is 4 minutes. The game takes hours and hours to run to finish anyway. And what is the crucial thing that you need to learn about speedrunning? You're not going to beat the game by smashing the buttons slightly faster. You do not speedrun Super Mario by doing what everybody else is doing, but like a tiny bit faster. You go to this by kind of finding a different path in the state space and kind of find ways that nobody else has thought about to solve the problem. Okay? And that's the metaphor that we're going to go with today. So you may think, okay, wait a second. Did you say lakehouse? If you Google lakehouse, you're going to find other fine folks that try to build one on the internet, right? So the small player in this space called Dremio, which is a couple of $1 billion companies. Then there's Snowflake, which is worth $75 billion today because they said AI many times in the earnings calls. Then there's the Databricks, which is worth $100 billion if you believe in the VC ability of accurately priced private company. And then there's Fabric, which is Microsoft, so whatever that is. And so this is where we are. This is not a scale because I'm bad at math, but you kind of get the idea. So how the fuck do you speedrun an entire lakehouse, right? And again, remember, you're going to speedrun a lakehouse. You're going to try and beat the game, not by doing what everybody else is doing, but slightly better. And I'm not going to name names, but Microsoft. Okay? You're going to try and speedrun the lakehouse by finding a different path in the design space that nobody ever thought about. And the two lessons that I'm gonna tell you about is that this is how we speedrun the lakehouse. One, by betting on simplicity, and two, by betting on composable data system. So the normal lakehouse, the lakehouse that you can find on the market today, have many good things going on for them, but simplicity is not one of them. So if you Google how to get started with a lakehouse, you're going to find many videos like this one. Okay? So this is a 4 hours and 17 minutes tutorial to get started with a lakehouse. But that's the funny thing is that at minutes 19, no shareholder value has been produced. Like, you're still trying to understand whatever the fuck this is. This is obviously like an explanation of how Spark works. Okay? So 19 minutes into the job, you have no idea what you're doing, and maybe in 4 hours, you're going to figure out something. Okay? Why is that the case? That's the case because historically, lakehouses have been developed by basically adding new infrastructure and new abstractions every time there's a new use case. Oh, you need to run a SQL query interactively. Oh, let's build a warehouse and give you an editor. Oh, I need to develop a pipeline. Oh, let's spin up a notebook, pip install stuff into that, and then run a cluster. Oh, I need to run stuff at night. Oh, I need to spin up a Spark API. I need to submit a job. I need to have a scheduler. Okay? Every time there's something new to do, you're just going to build something else, and you're going to ask your user to move around a million different UI and a million different abstractions to get the job done. In fact, in most lakehouses today, you need different teams to even bring one thing to production because the mental models are so different across the entire spectrum that it's impossible for one person to manage it all. And I want to show you, just because it's so much different than anything else, it's not going to take 4 hours, it's going to take a few minutes. I want to show you what it means to run one thing in Bauplan. Not because it's very important about Boplan per se, but again, maybe because it's a lesson and everybody here building system can bring somewhere else, hopefully. I hope you can see, because I don't know how small it's going to be. Sorry, the good thing is that if you don't believe me, you can go on Boplan Labs, you can create a free account, and you can try exactly what I do today. So in Boplan, you can just write functions in Python. There's a function called parent and a function called child. The child function takes as input the parent function, as you can guess. This is just normal Python function. The parent function takes as input different table, the taxi dataset and taxi zone dataset. And you're going to work from the terminal, like in Docker. In this case, we're going to check out a data branch, which is like Git, but for your data, so that we can sandbox our changes. Do you want to know the schema of a table? You can just ask, like in Docker, this is the table, taxi zone. Do you want to run the pipeline? You do Boplan run, the system spin up in the cloud 2 containerized function and start streaming in real time all the data. This is all in the cloud that happens in real time. This is not speed up. So the system now is reading data from S3, it's like 6 million rows, building 2 containerized function, sending data between 2 of them, and then creating a function at the end. You can get the function at the end, the child function, that has been materialized here. You get tired of Python 3.10, you can do Python 3.11, you can change polars, you can add 1 month of data. How do we rerun this? It's like code. You just go back to the terminal, you do Boplan run, and the system is going to rebuild all of this again for you. In 100 milliseconds or so on, a new container with a new version of Python, new version of polars is ready. Now we're going to run 20 million rows or something like that, end to end, in, I don't know, maybe 12 seconds. Okay? And at the end of it, again, like Git, but for your data, you're going to check out into the main branch, which is the production version of your data, and you can merge the artifact that you just did. You probably have never seen Boplan before. Many of you have never seen Boplan before. But you can probably already sort of see what's going on just because, you know, these are the normal abstraction that all software engineers work with today. Okay? So faster than the time that it takes you for you to figure out how to log in into Azure, you can run hundreds of millions of lines, pipelines in production in the cloud with Boplan. So how do we build that? And so the first intuition is like, can we get a unified model of how we run things in the cloud instead of what everybody else is doing? And so you saw Boplan being a Boplan pipeline being made of functions that are basically just chained together. Okay? And that's kind of intuitive, right? What is a data pipeline? Data pipeline is a DAG, is a series of functions, one of them sending the result back into the next one. Okay? So there's going to be some function defined by the user, of course, and there's going to be some function you system people probably figure out that there's some magic behind the scene. So when the function says, give me that table, there's going to be something that happens behind the scene to provide that table. But those are functions as well. Is a function that reads Iceberg, and the other one is a function that writes Iceberg, okay? And that's sort of trivial. I think everybody will believe this. What is a bit more counterintuitive is that you can also think of querying, like launching a SQL query, as basically a pipeline, okay? So what is the input? What is the first node of a SQL query is the table that corresponds to the IO scan that you can push down from a SQL query. So you get a SQL query, you can push down the scan, and that's going to be, again, our nice function that reads from Iceberg. And what do you need then? You need another function, which can be, in this case, a flight server, because we use arrow in flight, that basically communicates and streams the result back to the user. Okay? So even a query, even an interactive synchronous job, can be decomposed into a pipeline of different functions that basically keep on just sending each other small data frame-like artifacts. Okay? When you combine all of these together, you get what experts in architecture call the only FaaS model. Okay? A model in which the only thing you do are function as a service. Okay? And this gives you a unified mental model for running everything. Okay? So you can run a synchronous job, you can run pipeline, you can run job on the on a schedule. Okay? And so this whole situation here that you had before is not a thing anymore. So if you believe that, you know, now the only thing we need to do is run function, we need to do 2 things with function. We need to run them fast, as you saw in the video, and you need to schedule them properly. Okay? And we don't have time to talk about scheduling, but we're definitely going to talk about how these functions are built so that we can learn how to do that yourself, if you wish to do so. So when the user specifies declaratively what is the environment they want to have available for their function, in this case, Python 3.11, whatever version of polars, there's a control plane that basically takes that requirement and builds the entire chain of dependencies, package by package, explicitly into that. It doesn't do anything. It just builds the graph. And then what it does is send this to the worker, which is sitting somewhere in the customer cloud, okay? and tells him to install one by one in different functions that are completely sandboxed, all of these packages and all those dependencies. It's up to the worker to do a diff between the package they already installed, the package that may be available on the cache, and the package that actually is new to install. And then when we run things, we do not build a Docker container. We just take basically an empty container with the interpreter we need, and then we mount the package corresponding to the Python environment that the user wants to happen inside of the container in read-only mode. Okay? And this means that the container now takes 100 milliseconds to start, and then even when you need to download new packages, you're kind of like leveraging, the bandwidth of the cloud. Plus, remember that even if two top-level packages like Polars 8 and Polars 9 differ at the higher level, most of the dependency chain is actually the same. Meaning that if you achieve this level of granularity in planning, you end up just installing very tiny difference even when people iterate on that. And that's how you get, with standard Docker container, the type of experience that I show you. Okay? And this was not our idea. This comes from, at least that I know of, know your system literature, from a paper by the group of Ramsey and Andrea and University of Madison, Wisconsin, called SOC containers. Okay, and they're the first one to identify, in a similar way, it was not exactly the same, but to identify kind of like the underlying mechanism for you to do so. What's cool about this? Well, for the user doesn't have to install Docker. They can just use the Boplan client. There's no bandwidth bottlenecks. Everything happens already in the client. There's no ECR to wait for the update. Okay, for us as system builder, again, simplicity. We don't have to remember absolutely fucking anything. A function can spin up, can do the job, and can die. Do you want to run it again? It's going to be a new container. Containers are so fast and so cheap to build that we can just build them on the fly. We don't need to keep them around. We simplify a lot how we reason about the system. So if you put all of that together, you're going to get a much, much, much tighter developer loops compared to either a standard FaaS or a standard Python lakehouse like Snowpark, for example. Then the second thing you need to be fast at when you run pipeline, of course, is moving data in and out. Okay? Normal FaaS don't really do that. Like if you try to build something like this on Lambda, you need to go back to object storage all the time. I mean, you'll probably just exhaust Lambda's limit way before this. But even if you try to do that, it's not going to be very fast. The way in which we do so is by basically using arrow everywhere. Okay? So arrow is our format over the wire for between function communication and function to user communication. You may know arrow as the zero copy data format. Maybe many of you know that. And when I came to know about arrow, which was like a few years ago when we started the company, so I come from a background as a failed logician, and so I thought when I heard the first time zero copy, that zero copy means zero, like zero. It turns out that zero copy is kind of a bullshit marketing term in the system community, and it means sometimes one, sometimes two, but never really zero. Okay, but arrow is the closest thing that gets you to that deal. So if you think about typical ways of moving, stuff between two different functions that are completely isolated, the typical situation that you find in Boplan is going to be B or C. So B is you have different workers and you need to send tables between one of them. And it actually turns out to be that sending arrow between EC2s at bandwidth speed of AWS is as fast as reading a Parquet file locally. So it's very, very fast. But of course, when you collocate can function, you can actually do the trick of sending memory object into shared memory, and then all the children can memory map them with zero copy. I mean, there's still one copy, technically. And it's a good research question, which I'm going to leave you as an homework for the audience. It's like, can you even do D? The true zero copy. You see, this is really zero copy. This is zero. Okay, there's no copy there. Okay, can you do D? And the answer is like maybe. And if you're interested in that, there's a paper called Zero, which is zero copy arrow, with the University of Madison, Wisconsin, and ourselves that shows how to do a trick in the Linux kernel to kind of fool the Linux kernel to not produce any additional copy. But that comes with additional cost. So what is the second lesson? So what is the second lesson of speedrunning things? Is reusing what other people have been doing, which is perhaps a trivial thing in the software community, but it's really not in the data community. So when you run Boplan, like a single Boplan run, the thing that you saw that runs so seamlessly, have hundreds of traces that span dozens of calls between backend systems that comprise hyperscaler paths to obscure library you never heard before. Okay? And so Boplan was built around the idea, which is the composable data system manifesto, that you can focus on whatever you think is your core competence. In our case is the runtime with the abstractions, like the thing that I show you. And you can almost reuse everything else for the rest of your system. So if you look at Bowplan, our query engine, the ephemeral query engine that I showed you before, used to be a fork of DuckDB. Now it's Data Fusion. Our catalog is a fork of Nessie. Our Duck planner is built on Kuzu. Our Iceberg client is based on PyIceberg. Okay? That is the idea that instead of rebuilding everything yourself, you can get started with a lot of things that are out there and kind of like, make them a bit nicer to work for the user. However, composability has an interest rate, which is very steep. You get to market much faster, and you get to not redo a lot of stuff that you don't believe are the core of your product, but it's actually very, very hard as you scale your company and you scale your use cases. Why? Because every time you add an open source project, you need to be part of that community. You need to know the people. You need to understand the project. You need to understand who's the contributor, what's their style, what they want to do. You need to adapt and improve it. Many of our projects that we adapted at day one, they didn't scale for the necessity of our system. Our typical example is Nessie. Nessie was fine at day one. Then we quickly turned out to be the biggest Nessie operator on the planet, much bigger than the company that invented it. And Nessie just didn't work at that scale because it wasn't really thought for that use cases. So you have to change it and massively modify it. And then, of course, it's part of our duty as good citizen of open source and the scientific community to give back to the community. So every time we find a bug, like today in Data Fusion, for example, we open an issue and we try to work with the community to fix it and upstream it. So when people think about how you run a company that has so many dependencies, people tend to think of like a one dimension, which is how dependable is this dependency. But I think there are actually two dimensions, which I call the dependency plane. So this is the obvious dimension, which is how battle tested this is. Okay? And this is the other dimension which I like to add, which is how can I infect things myself? Okay? And this is really what's important when you build something. So this is a trivial one, but this actually tells you a lot of when you need to defend. And our company, dependency, kind of falls, almost all part of this design space, right? From incredible, stable, but things that you can never touch, S3, to like sort of very experimental and things that we built ourselves. So we can change everything here, plus everything else in between. So how do you do that? Well, there's a lot of things that you can do to build a reliable system, ranging from left to right. How a pain is this to do? Unit test, end-to-end test, simulation, and formal proof, and we do all of them. So we unit test not just the thing that we build ourselves, but we actually add tests to open source components that we don't fully trust because they're too new. We run end-to-end tests with everything. We build simulators for the policy of our scheduling. So we have a simulator that actually simulates when you change how to schedule function, the throughput and the latency of this new policy. And we do, which is what I'm going to do today, a deep dive on formal proof. So we actually do and some work in actually making sure that our system is correct by definition, so to speak. Okay. And I'm going to skip to this. So what is the worst pipeline? The worst pipeline when you run is the pipeline that is half done. Okay, so this is a pipeline which has a source, an intermediate data, and a final state. Doesn't matter. You have one line here is main, is your data branch. You have a source, intermediate, and then something happens there. Okay, why this is bad? This is bad because this table is completely atomically changed because it's Iceberg, but the full pipeline is not consistent. Like some people reading from this will find that this is changed, but this is not. Okay, and this is like the worst possible solution. Okay. So can we get a page out of something that we know of to actually go and fix this, right? And so if you think about this typical database system, the database, the tiny vertically integrated Postgres that sits on your computer, these are like very nice. Like, they control both the storage, they control the writes and reads, and combining the control of writes and reads and storage, they're able to provide what is basically concurrency control. Right? They're basically able to provide the fact that if you run many things and something fails in between, the consumer, the other people, will either see the entire results of your changes or none. Okay? And so if you really squint a bit, you can actually try and see how concurrency control in standard database in MVCC is very, very similar to Git branches in version control, right? These are both ways for you to basically do changes in a concurrent fashion. There are both ways for you to manage conflicts, and there are ways for you to shield other people from any stupid mistake you may do. So can you do this in a fully distributed system that is not like a tiny Postgre that is sitting on your lap? But Bowplan is kind of like this. A Bowplan DAG may be a monstrosity of 100 nodes with 3 different Python interpreters, a SQL function that runs for 3 hours. Like, it cannot be further from the tiny Postgres job that you run on your laptop. But can you give people the same guarantees? And the intuition here is that if you combine writes and storage like a database does, you can actually do that. How do you do that? When you run, you can open a temporary branch. You can materialize all your states there. And then at the very end, you're merging atomically all these 2 tables. And when things go fine, of course, whatever. But the important thing is when you fuck up something. Okay? So when you fuck up something, you have opened a temporary branch, source is a 0 copy of this, and then this table here does not get seen by anybody else. So downstream consumer in any point of this time basically act like I never existed. This can take 3 hours or 3 minutes, but it doesn't matter. The system just does it. The nice thing also is that this is, unlike a database transaction, this is not really ephemeral. There's going to be a Bowplan branch that you can check out with that points to some real file in S3 when you can use to debug the system. Okay? Which also means that we can guarantee to any consumer that if by an act of God, an EC2 gets trashed in between a pipeline, nothing happens to the data that they have. They may have to rerun things, but there's no consistency issue. Of course, we've done a bit of work in formal modeling with a tool called Alloy to verify a bunch of the process. Some of these have been open source. Some of them will be open source in the rest of the year. And we kind of have this like tiny proof that you can actually think of MVCC and Git as kind of like 2 faces of the same coin. And of course, I have a fantastic proof of this, but this slide is too small to contain it. Okay. What is the cool thing about proof? So Bertrand Russell, one of my favorite people of all time, says, well, the good thing about proof is not that they make you more certain, that they should make you more skeptics, right? And in fact, when I say to you that MVCC and Git for data are actually the same thing, you should actually be pretty skeptical of this claim because it's kind of like an absurd claim. And thanks to tools like Alloy, for example, or Model Checker, by investing in all of this, you can find out actually abnormal cases that will invalidate what I just said. Okay? So Git for data, if left unchecked, like if you take the analogy of Git and Git for data too much, you will actually break the MVCC concurrency, and this is a counterexample, right? I can have a temporary branch that Jacopo did, and this died because of a mistake, but then Luca, without nobody knows, this distributed system is gonna branch and merge, which will result in a bad merge in main. So if you don't add additional checks to Git, Git is sort of like, a bit less constrained than what MVCC does. Of course, we barely scratch the surface. So there's way more things to do. I'm just going to leave you with one more suggestion, since everybody wants to do AI these days. So there are 2 things there are 2 directions. Like one I think is less interesting. I think one is actually genuinely interesting, but they're both kind of like part of the zeitgeist. So system for AI, like you build system that some AIs can use. We just published a paper. It's called Safe and Trusted Agents. And what's the gist of it is you want LLM to reason about the code with APIs. You want the LLM to have sandbox to write their data to. You want LLM to make mistakes. All of these things is already true in Bubble. We don't have to build absolutely anything. We already have functions that are fully isolated. We already have branches so that you can fuck up there and nobody is gonna notice. And we have very simple APIs, the one that you saw, that an LLM can learn. So if you're interested to see LLM doing real data engineering work, this is today possible. Like, this is possible today. But I think that's a non-interesting thing. The more interesting thing, which I think is actually a bright future in the community, not just in our company, is the opposite, is AI for systems. So AI, as you may know, has been having incredible success in things like mathematics, right? And why is that the case? Because mathematics is an objective answer. Like, it's very easy to verify when a theorem is correct or not, right? And there's a lot of areas in systems. For example, let's say you build a simulator of your system like we did, where now you have sort of an oracle that you can poke very easily. So today, we can unleash a code generation tool like GDP5 and use a verifier that takes a second to tell him, hey, this policy is good or not, to generate better system policy than the one we can come up with manually. If you imagine the entire design space of system that people built, or data structure that people ever invented, we are probably explored as humans such a tiny fraction of this universe. And to me, one of the most exciting things about AI is the fact that we can now have somebody that explore promising path in this gigantic universe and finding things that we will never have found ourselves in a reasonable time. Because how likely is to be that the few data structure that we figure out or the few distributed system abstraction that we have are the best one that we can have? How likely is that the case? But if somebody can help us with this, I think it's a fantastic use of AI. And all of this starts from API, simulation, and a formal verifier. If every time I need to run ChatGPT, I need to spin up my entire system as a copy, it will take years anyway to do it. So we need to have a way to speed it up. If you want to know more, again, there's a bunch of papers that you can read if you really have trouble sleeping at night, ranging from data, systems, and the latest stuff. Summing this up, these are the lessons that we learned by speedrunning a lakehouse. So first, contrary to most opinions, many of the use cases of data workloads can be actually summed up as chain freaking functions together. Doesn't mean all of them, but a gigantic part of data workloads can be summed up of that in the all. Second, composability is great. Again, allows you to move faster and explore design space quickly, but it's not as cheap. I mean, it's cheap in the beginning, but it's like a credit card. Then the interests are like pretty steep. So, thanks. So I'm gonna close with a sentence from one of my favorite persons, Ardi, the mathematician, not the actor. And it's not worth an intelligent man's time to be in the majority, because by definition, there are already enough people to do that. Thank you very much. Happy to answer any question. Please, do you want a mic? Yeah.
Can you talk more about how you design and build the simulator?
Yes. Which is, by the way, is open source and published. So we are very happy to check it out. We worked with people from the University of Chicago last year to build this simulator that takes as input. You can either parameterize traces from like imaginary data workloads, depending on some statistical parameters, or you can inject some traces that comes from the real system. And that's an event loop as a deterministic, basically, execution that will take the function, will simulate how long they take, and then it will simulate how much resources they do. You can run it for a parameter, like how many minutes or hours you want, and then it will spit out a few things that you care about, like throughput latency, how many jobs need to be retried, and all of that. The simulator is generic, and it gives you a Python class that you can subclass, and that is the policy. So the scaffolding is the same, and how do you try your simulator? You basically implement an interface in Python. You write whatever logic you want about allocating memory, CPUs, whatever, and then you press a button. And then the system will basically do the scaffolding and the statistic for you. And the way in which you do with an LLM is basically ask the LLM to produce that, and then you inject it in a real system, you get the output out, and then you continue to do so, and you hope to get something that is not completely stupid out of it. Make sense?
Makes sense, thank you.
Any more question? Please.
You talked about the cost of open source, and I think you mentioned Kuzu.
Yeah.
And am I mixing them up? Is this not the database project that just like shut down?
Yeah. So the question is like you mentioned open source, and Kuzu was part of the presentation. Is this the open source that got archived? Yes. That was a fun week in my life. That is correct.
Are you forking it and supporting it now, or what?
I mean, this supporting like a C++ experimental graph database in memory. It's a bit too much for a company of 9 people that have other stuff to do. I know the community have been trying to fork it in a few directions, so we'll see how that goes. That said, we're by far the biggest users on the planet. So every time you run, so Bowplan now runs hundreds of thousands of times per day, and every time there's a Bowplan run, inside of it, there's a tiny Kuzo memory database that gets created and then gets destroyed. So it's also fairly stable. I mean, at our scale, it's actually fairly stable, but it's not going to be, unfortunately, pursued anymore by the original team. But that's another part in the diagram of life. In fact, Kuzo is like bottom left, right? Like, how can I infact this myself? I cannot. How dependable it is really not. And I was right. I mean, this slide was actually built before the problem. So yeah. But on the other side, is there any alternative? Like, will I develop myself, something like that? And the answer is like, there's just no way that we can do that. And so maybe we're going to go with one of the more either established vendor or change it if it becomes a problem. But for now, it's actually very stable. So the latest version that is out today has been working fine for us. So I guess it will work fine for most people. Please.
What's on the roadmap for the future?
For us, well, a million things. So we need to improve. We need to improve our scheduler like significantly because as we start ramping up many more customers, this becomes kind of like like a main issue of contention. Once you reduce all the problems of a lakehouse to function, then really that is the only problem that remains in a sense. There's a few other problems, but those others are kind of like boring. And the other part is like improving our SQL support. So we support querying, not in the sense that Snowflake does, but we support query for like, small experiment or stuff like that. And we just moved from DuckDB to Data Fusion actually today. There's a story behind it that we're going to write at some point. And SQL is kind of a drag. Like, because at SQL, you're not judged by your average thing, you're judged by the long tail, right? And so you move to another system, and the vast majority of queries will work at day one, but then there's this tiny thing that doesn't, and then people will bother you for that. This is a combination, I think, of like, just how SQL people operates, and by the fact that the bar in SQL is much higher. Like, if you want to run Python on your data, I think Bowplan right now is so much better than any alternative of the platform that I show, that's fine. It's not perfect, but on SQL, you're competing as Snowflake, which is the best query engine on the planet, right? So, and you don't need to be better than them, but you cannot suck too much. You know what I mean? And it turns out that it's very easy to suck at SQL. Right? And even very popular open source projects like DuckDB or Data Fusion, which are great for many things, we're very grateful to contribute back, blah, 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 but they're very far from the reliability that Snowflake gives you. And we hope to, by having so many customers finding bugs immediately, we are actually already upstreaming some of them. So I think this is good that other people are joining the Data Fusion, bandwagon than Paul pioneered a few years ago. Because the more customers we have, the faster we find bugs that we fix for everybody, and so that's kind of help everybody. But it's much harder than what it looks like. So yeah, you know what they say, like we don't do because it's easy, but because we thought it was easy. So I saw a hand there, but I didn't see how. Please.
Do you have any fun anecdotes of SQL compatibility issues that you, or like bugs that you run into?
Do you have some fun anecdotes? That's the. Oh yeah, like quite a few of them. So there's the easy issues and the hard issues. The easy issues are, we told our customer they need to switch dialects months ago. They didn't. Of course, that's fine. And so there's a long list of things that DuckDB just does slightly different because of syntactic sugar, and Data Fusion does in a different way, and at day one, they all fail. Okay? So you get this report of like, oh, my dashboard, these 10 queries and fails. Like, no worries. It's all under control. There's a thing here that you need to move, and a thing here that you need to move. And that's the easy part. The hardest part, then there's like medium level, which is something that is technically not, maybe it's wrong, but it's kind of weird. For example, we find out that if the customer encode the URL path in S3 with a % like Ive, but it's double encoded, Data Fusion gets tripped on that, and it thinks that it needs to revert it. And so it doesn't really work. So we already fixed that. Again, this is, it's not really a bug, but it's kind of like an edge case that, if you have real customer, you're going to find out at day one because not everybody has pristine S3 Parquet files. And then there's the gnarliest one, which is the one that we, other found today. It was like, no, this is an upstream bug. The optimizer, the analyzer is doing something obviously stupid. This query is correct. And then there's nothing you need to do. But I would say, 95% is syntactic sugar that you take into account, and the first week is just going to be a roller coaster, and you're just going to fix them, help your clients move. And then the other 5% is between things that are like sort of a bug and things that are really a bug. But yeah, the other things that is very hard for building composable system is that the customer doesn't care. Like the bug is in Data Fusion, not in Bowplan. It's not an argument. Like, people buy Bowplan, and it's part of our, mission to make sure that things are good. That's why we invest so much in testing. That's why we have all type of testing possible. And when we used to have Kuso, we probably have more testing than the actual Kuso team. They actually ask to run our test before every release because how good our tests are. Because again, not because I don't trust them, but because I'm responsible in front of the customer for what they do indirectly. And so I need to be very careful about that. And I'm sure at Data Fusion, we're going to do that as well. But yeah, so what I save in development time, in part I pay in testing time that I need to do. Any more questions? Good? Cool. Thanks so much for coming out. I know this is not San Francisco, so you have actually alternatives to actually do. So thank you very much. I really appreciate it. Thank you.